So I'm going to do this first day of L'Hopitals with you because I have to be at this meeting. I would much rather be with you, so I apologize. I want to remind you that we will have an AP problem on Thursday. It'll be AP number 7. It will not be on Newton's method or L'Hopitals, which we are going to do, and it will be in what we're going to do today. And AP 7 will be traditional partners, not the modified partners that we did AP 6 on. And then we'll have the first part of the test on Friday. So today I will do the first part of L'Hopitals, and Wednesday the second part of L'Hopitals. On Thursday we'll do AP 7, we'll do our little book, and I'll take any of the, we'll have some time for you to work together and ask me questions or look over the solutions on that review, on the Unit 4 review. Okay? These book problems shouldn't be too bad. Tomorrow's book problems will be a little nastier. This particular warm-up problem, if it showed up on the test, would be on the calculator part of the test, simply because the function involves e, so you're not going to be plugging in a bunch of values of e without a calculator. But if the objective of the question is Newton's method, you must show that you understand Newton's method. So to do that, they're giving you the first guess of 0. So set up Newton's method by saying that x sub 1 is going to be equal to x sub 0 minus the ratio of y at 0 over y prime at 0. Now this actually turns out to be a rational number because y of 0 is what? If you plug in 0 here, you get e to the 0 minus 3, right? So that's 1 minus 3 is negative 2. And then y prime is 3e to the 3x. And if you put 0 into there, you just get 3, right? So this is actually 0 minus negative 2/3, which is 2/3. X sub 2 then would be 2/3 minus y of 2/3 over y prime of 2/3. You certainly, without a calculator, are not going to be generating that. And that answer is 0.46866. They're asking me to be correct to 4 decimal places, so I just have to keep running through this until I get 4 decimal places to repeat. So I was starting to feel bother. I think this is x sub 0, this is x sub 1, 2, technically 3, 4, and then x sub 5 was where I got it to repeat again. Again, please don't take too much stock in, whether those are x starts at x sub 0, x sub 1, whatever. I don't even know. I can't keep it straight myself. When in doubt, go one more than you think. Okay? Please don't stress. You're not going to lose points for that. What you are going to have to show here to get full credit, you're going to need to show Newton's method formula one time, right? One time. And then you're going to have to show some of these answers. You're not going to have to write this again. You're just going to write, and I'll tell you when to stop, or if I say 4 places past or whatever, just, like I said, go one more maybe than you think you should. I promise, no harm, no foul. All right? All right, so today's objective, really today's and tomorrow's, is L'Hopital's rule. And the objective, what L'Hopital's rule objective is to evaluate limits. And you say, wait a second, evaluating limits was Unit 2. Okay? But I want to evaluate limits using L'Hopital's rule. And to use L'Hopital's rule, you need to know some derivatives. And that's why we waited until now. We couldn't do it in Unit 2. I just do want to remind you that in Unit 2, to evaluate limits, first you plugged in. If plugging in didn't work because there was a continuity issue, you did algebra, or you did maybe some trig, or you used a calculator, or made a table, either on your own or with a calculator, to try to figure out what's going on, and then you re-plugged in. Right? I do want to remind you too that I told you just to memorize that the limit as x approaches 0 of sine x over x was equal to 1, right? Told you I can't show you why that works, but just to memorize that. And it is worth memorizing, but I'm going to show you today why that works. So there's L'Hopital. Guillaume is his first name. What a cutie, right? He was wealthy. He was part of the aristocracy, I believe. And he was super interested in math. And so he could only go so far on his own, though. So he hired, because he was wealthy, a tutor. And his tutor was one of the Bernoulli brothers. The Bernoulli brothers were not poor, but they were working, right? And they had to, I think they were a professor, maybe one or two of them. I think there was some brother-sibling rivalry or whatever. Everybody wanted to be published. So did Guillaume. So he discovered an application of derivatives to evaluate limits of a particular form when you ran into problems, continuity problems. But it actually was with the guidance of his tutor Bernoulli. But Guillaume did get a book published, and Bernoulli was a little bitter that this was named L'Hopital's rule. But L'Hopital did give him props in the preface of his book. But if we really want to make Bernoulli happy, right, I guess we should call this Bernoulli's rule. Womp womp. Too bad. Nobody thinks of it as Bernoulli's rule. All right, so first I'm going to talk to you about a Unit 2 problem. In Unit 2, we looked at this problem, we plugged in 2, and really, we focused on the denominator. We said, oh, dagger, the denominator is 0, gasp, I have a continuity issue. I'll use algebra. And in this case, algebra worked, right? You were able to factor and cancel because this discontinuity ended up being a whole. Right? And as with a whole, we were able to see that the function leveled off on both sides of the whole. The important thing, though, is now we have to consider not just the denominator being 0. It's important to know that we also get 0 in the numerator, right? If you plug 2 in here and here, we don't just get division by 0, we get 0 over 0. You need to know this vocabulary. That's called an indeterminate form because I can't determine what 0 over 0 is without more information. 0 over 0, is it 1 because it's anything divided by itself? Is it undefined because it's something divided by 0? Is it neither of those? I don't know. I can't determine without more information as to how did 0 over 0 happen. And that's why that is called an indeterminate form. Since this indeterminate form can be evaluated by factoring and canceling. And I get 4, again, meaning that graphically what's happening is that my function looks like x plus 2, except at 2 there's a hole. That's supposed to look nicer than that. And the value of the hole is 4. What that means for the limit is as you approach 2 from the left and as you approach 2 from the right, the height you're approaching from both sides is 4. But let's pretend I didn't know that. Let's pretend I didn't know algebra or algebra couldn't help. This limit, it's important to think about this limit as being a ratio. Now it's being a ratio of a parabola to a line. Both of those are differentiable functions. When I look at the two functions separately, right? Not the ratio. I look at them separately, right? There's the linear function. Here's the parabola. At 2, both of their values appear to be close to 0, or maybe they are even 0. They're not. They're close to 0, right? As you approach 2. At 2, they're 0. But we're not, remember, a limit isn't actually about what the function is at 2. It's what happens around 2 on both the right and the left. And then further, this limit is about the ratio of those values. Because both of these functions are differentiable, if you zoom in close enough, the line, shocker, stays like a line, but the parabola also looks like a line. Again, the separate values of the line and the parabola look to be 0 at 2 and close to 0 when you're around 2. What's the ratio of those values, though? Not the value 0, 0, but as you approach 0 over 0. Right? So yes, the intersection looks like 0, but I want to talk about the ratio of each one of those. And if you doubt me, I doubt you, I challenge you to get your calculator out, type in 1.9 squared minus 4 divided by 1.9 minus 2. You ain't going to get 0. The ratio, both of those numbers are close to 0, but you know what the ratio is? Not 4, but close to 4. Crazy, right? It's the ratio that's the important thing. So again, let me make that even bigger. Since I can think of these functions as their tangent lines as I get close, right? That green height here, right? There's the change in y, which is also the change in the tangent line as long as I am really close to x. Here's the change in y of f, right? So I'm talking about a y value in f compared to a y value in g as long as I'm really, really close to 2. But since I'm zooming in and both of these functions are locally linear, I can also say that those heights as I approach 2 are also the heights of the tangent line of f and the height of the tangent line of g. But the tangent lines are just what? Derivatives. And of course the dx's cancel out. And so what I really have is a ratio as long as I started out 0 over 0 this ratio becomes the same as f prime of x over g prime of x. Whoa. Here's another proof of that statement. Here's what L'Hopital's rule says. Given that f of a and g of a both are equal to 0, that's important. Given that f and g are differentiable and that g prime of x isn't 0, then looking at the limit of the ratio of f to g, given that, right, at a, given that that will become 0 over 0 because f of a is equal to g of a and both of them are equal to 0, that instead of looking at the limit of the ratio of the functions, I can get the same result by looking at the ratio of their rates of change, or their tangent lines, given, of course, that the limit exists, meaning that the right and left-hand limit are the same. So the proof I'm going to do is actually going to start with this and manipulate back here, just using algebra and my givens. So if you remember from the property of limits, the limit of a quotient is a quotient of the limits, and the limit of x approaches a of f prime, that's just the definition of derivative. So that's f of x minus f of a over x minus a, and g prime is the limit as x approaches a of g of x minus g of a over x minus a. Well, guess what happens to the x minus a's? Bye-bye. And then back here again, what did we say f of a was equal to? G of a. And what were they both equal to? 0. So what I now have f of x minus 0 and g of x minus 0 with, bam! Starting with the limit of f prime of x is equal to g prime of x, I can prove that is the same thing as the limit as x approaches a of the original functions, given that what? That only works if f of a is equal to g of a, which is 0 over 0. That's really important. Now, if both of those previous, that graphical explanation and this kind of algebra proof explanation stress you out, forget both of them. Just memorize that when you plug in a limit, when you're evaluating a limit, and you get 0 over 0, you get 0 over 0, you are allowed to replace the numerator with its derivative and the denominator with its derivative and re-plug in. So the derivative of x squared minus 4 is 2x. The derivative of x minus 2 is 1. And I get 4, which is what I got with the algebra, right? So you don't have to remember that proof. You don't have to remember that graphical explanation. You just have to memorize that if, this is super important, if the limit of a ratio is indeterminate, then, and an indeterminate of the form 0 over 0, then you can replace the limit of the ratio of the functions with the limit of the ratio of the derivatives. So, for example, when we were doing the limit as x approaches 0 of sine x over x, we plugged in and we got sine 0 over 0, which is 0 over 0. That means I can L'Hopital. Doing L'Hopital means I can take the derivative of the numerator, the derivative of the denominator, and re-plug in. It's just, for some reason, AP likes sine x over x and sine 5x over x and blah, 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 blah so much. It's worth just memorizing the pattern. but you can always L'Hopital it. That's why it works. And I just couldn't tell you that in Unit 2 because you didn't know derivatives yet. So let's look at this example. With any limit, step 1, plug in. Step 2, do you get 0 over 0? If you get yes, L'Hopital and replug in. Love. So step 1, plug in 0. I plugged in 0. I got 0 over 0. I've got hope. I'm going to lope. That means I'm going to take the derivative of the numerator, the derivative of the denominator, and re-plug in. The derivative of, sorry, get rid of my crazy erasures. So I took the derivative of the numerator, derivative of the denominator, and I re-plugged in. And I got 0 over 1. This is not indeterminate. 0 over 1 is I don't need any more information to determine what is 0 divided by 1. 0 divided by 1 is 0. Stop. I'm no longer indeterminate. Now I want to show you that what happens was sometimes people get so psyched about L'Hopital that they keep going. So what happens if I just was indiscriminately saying, oh, I just feel like I just want to L'Hopital some more. So I wrote that, oh wait, ignore that for a second. I wrote that down, sine x 1 plus 2x, and I was like, oh, I just want to L'Hopital again, and oh, now I might as well stop, and now I'll replug in. I replug in and I get a half. But the problem is that here, this was 0 over 1, which was not indeterminate. So I could go ahead and do L'Hopital, but I get nonsense out of it. And what I'm trying to show down here with the calculator, right? If you put the numerator in y1 and the denominator in y2, turn them both off, and then graph y1 divided by y2, or just put it all in y1. That's kind of easier now with the newer software. You can zoom in or use your table, and you can see that the limit is not a half. The limit is 0. This function has a hole. This function has a hole at 0, 0. And as you approach 0 from the left and you approach 0 from the right, the function values aren't 0, but they're close to 0 on both sides. On the other hand, there are some times where you do have to keep L'Hopitaling, which I just turned into a verb, because you do keep getting indeterminate forms, and that's the key. The key is whether you get indeterminate form. So copy this example down and convince yourself that you get 0 over 0. Notice I don't really say I shouldn't really say I get 0 over 0. I'm not really plugging in 0. I'm plugging in numbers really close to 0. So my numerator's approaching 0, but how? Quickly, slowly? How close to 0? So is my denominator. But how? Right? That's what makes this indeterminate. It matters how I'm getting 0 in the numerator and 0 in the denominator. So since I have 0 over 0, and that means I'm not sure what's going on, I have hope, or lope, as they call it. I'm totally making this up. Loping. I didn't do any math yet. I just took this radical and wrote it as 1/2. I'm going to have to chain rule this because I'm going to take the derivative of the numerator and the derivative of the denominator and then re-plug in. Here we go, Guillaume. So I brought the 1/2 down. I copied over the middle. I subtracted 1 from the exponent and got negative 1/2, and technically spit out the derivative of the inside, but that's just 1. The derivative of this constant is 0, and the derivative of this linear function is just this constant. And then, of course, the derivative of x squared is 2x. Then I re-plugged in. Guess what I still got, though? Guillaume. Come on, Guillaume, help me out again. So this time, I'm going to do the same thing. When I re-plugged in, I still got 0 over 0, so I'm going to take the derivative of the numerator again and the derivative of the denominator, and I already see that I'm going to stop L'Hopitaling after this, right? You see why? So I brought down negative 1/2, and I got negative 1/4. Copied over the middle, subtracted 1 from the exponent, technically multiplied by the derivative of the inside, which is just 1, and the derivative of 2x is just 2. And now I'm going to re-plug in. And again, if I don't have, see, I already knew up here that this was my last L'Hopital step, because if my denominator is a constant, there's no way that by plugging in I'm going to get 0 over 0. I might get 0 in the numerator, but I'm not getting 0 in the denominator. Right? So this is not 0 over 0. So I cannot L'Hopital. I plugged in and I got negative 1/4 over 2, which is negative 1/8. Which means this original function has a hole. It has a hole at 0, negative 1/8. The function never equals negative 1/8 there, but it approaches negative 1/8 from both sides. Now, there are other indeterminate, as much as I love 0 over 0, there are other indeterminate forms. Infinity over infinity we love. Now again, you might say, how come that's not 1? Well, it's because infinity is not a number, right? It's a description of function behavior. So maybe the numerator is e to the x. So sure, off to infinity, it goes off to infinity, right? But pretty quickly, as opposed to maybe the denominator is x squared. Goes to infinity, but not at the same rate. Infinity times 0. I thought anything times 0 was 0. Well, not sure if infinity minus infinity, is that 0? It depends. How fast is something going to infinity? Then I have exponential issues. 1 to infinity. I thought 1 to anything was 1. I thought anything to the 0 was 1. I thought anything to the 0 was 1. Okay, these are daggers. I'm going to give you an example of infinity times 0, and that's all your homework is going to be involved with today. Tonight's homework is either going to be 0 over 0, infinity over infinity, or infinity times 0. Tomorrow, we will deal with these other cases. Hint, how I deal with this is getting a common denominator, and how I deal with exponents is, you got it, logs. I call that, hey, what's up? I call this doing backflips. So if I don't have 0 over 0, if I don't have infinity over infinity, I have to do algebraic backflips to get myself into either 0 over 0 or infinity over infinity. So again, if I have 0 over 0 or infinity over infinity, I just take derivatives of the numerator, derivative of the denominator, replug in. But if I have infinity times 0 or any of these other cases, I have to get myself to a fraction before I can do L'Hopital's. So the next example I'm going to do, oh, there's my log. I don't know why my log is on a plate with legs, but that's what it is. So this example, the first thing you have to do is convince yourself that it approaches infinity times 0. So you have to recognize it's a product. So of course when I plug infinity into here, into x, that's infinity. When I plug infinity in here, remember I'm approaching infinity, so this is 1 over bigger and bigger numbers. 1 over bigger and bigger numbers approaches 0. Sine of something close to 0 approaches what? 0. So that's how come I have 0 times infinity, infinity times 0. Now let me remind you of something from elementary school. Isn't it true that 3 times a half could be written as 3 divided by 2? Isn't that true? Isn't it also true that 7 halves divided by 5 is the same as 7 halves times 1/5? Isn't that true? Well, I want a fraction, and I've got multiplication. So take this multiplication and turn it into a fraction. You need to reciprocate something. I suggest you don't reciprocate sine 1 over x. So there's my backflip. I took a product and I turned it into a division. Convince yourself that sine 1 over x divided by 1 over x is the same thing as sine 1 over x times x, right? I'll let you stew on that for a minute. Now, I took something that is infinity times 0, and what did I turn it into? Sine of 1 over infinity is sine of something close to 0. Sine of something close to 0 approaches, it isn't equal to, it approaches 0. 1 over infinity also approaches 0. It's not equal to 0, right? 1 over big numbers are never going to equal 0. It's an important concept. Now that I have 0 over 0, though, I have hope. Oh, gosh darn it. Bring Guillaume to the table. Again, you can look at this in your calculator and you can see the answer before Guillaume shows us what the answer is using your table or your zoom function. But I'm going to take the derivative of the numerator, the derivative of the denominator, and then replug in. So here is the original. The derivative of sine is cosine of the stuff times the derivative of the stuff, right? The derivative of 1 over x is negative 1 over x squared. Those cancel out, and I end up with cosine 1 over x. Plug infinity in here, right? Replug in. And cosine of 0 is 1. So this function has a hole. No, it doesn't. That's if I'm going to 0. I'm going to infinity. This is end behavior. This function's end behavior. Right as I go off to infinity, this function approaches. I didn't say equals. I said it approaches 1. Now I'm going to talk about using L'Hopital with a one-sided limit. So sine x over x squared, I only want you to evaluate the limit as x approaches 0 from the right. But I start this, I kind of ignore that at first. I just, right, the first thing I do is plug in 0, right? Sine of 0 is 0 over 0 squared. Right? I get 0 over 0. So I can take Guillaume, L'Hopital, bring him down here. Here's the derivative of the numerator. Take the derivative, and then re-plug in. You can't just say undefined. 1 over 0 is not indeterminate, right? This is not indeterminate. But I do have to think. Remember, you're not in Algebra 2 where you're just like, oh, you know, something doesn't exist. I'm not asking you about anything existing. I'm asking you about function behavior of sine x over x squared. I couldn't really think about 0 over 0. It's too confusing. But 1 over 0, I can think. So here's what I'm going to guide you. I'm going to show you how to think in this instance. So I want you to think of cosine of 0, but not cosine of 0. Cosine of numbers really close to 0. Those numbers are approaching positive 1. But that is a ratio with not 2 times 0, but 2 times numbers that are close to 0. So I have a numerator plugging in numbers close to 0 to cosine, which means my values are approaching positive 1. But here I'm multiplying 2 times positive numbers, but really, really small. So aren't I getting really, really small positive numbers? Your numerator is staying close to 1, but your denominator is getting smaller and smaller and smaller, but positive. What is this behavior? That behavior is going to positive infinity. Crazy, right? You do actually have to think. Now go to the left side. Do the exact same thing. It's a little too difficult to do thinking with 0 over 0. But I can use L'Hopital. Remember, Guillaume was right here. Bring him over. Take the derivative. I still get cosine x over 2x. I still get 1 over 0. Think. Your numerator isn't 1. It's really close to 1. Your denominator isn't 0. It's 2 times numbers really, really close to 0, but they are negative. So they're really small negative numbers. Numerator staying close to 1, denominator getting smaller and smaller and smaller. They're negative. This limit is asking you about the function behavior. How is the function behaving on the left side of 0? Since I didn't get a number, I got opposite infinities, this function doesn't have a hole at 0. What does it have? You just justified using calculus, not a calculator, not math. You just proved the existence of what? Right? As x approaches 0 from the right, function behavior is off to infinity. As x approaches 0 from the left, function behavior goes to negative infinity. Crazy, whack, funky, eh? So again, your homework is not so bad. You're going to start off with mostly 0 over zeros and infinity over infinities. For the beginning problems, the 3, 6, 9, 12, 15, and 17. Then I skip you over to some other problems. The wording is just probably a little weird, but you still are dealing with 0 over 0 and infinity over infinity in like the 30s. And then at the end, again, you'll recognize the problem as being, you know, some of the words of it are, I use an example from the lesson today in number 60. All right? So these homework problems shouldn't be too bad. It's tomorrow that's the doozy. But I'll be there tomorrow. So hopefully me in person is better than me by YouTube video. All right, I will see you tomorrow.
So you do it all over.